Hello! In this video we'll talk about focus stacking. We'll talk about the topic in general. I'll show you a couple of open source programs that we can use, and I'll show you the additional calibration that I did in my setup to get faster and more accurate results in the context of 3D reconstructions, at the cost of a lot more work. So let's get right to it and start with a few basics that we need to talk about focus stacking. So when we take a picture, then only objects at a certain distance from the camera are in focus. That's called the focus distance. Everything that's closer to the camera or further away gets successively more blurry. And blurry means that a point in the real world is not captured as a point on the image, but rather as a circle or maybe an ellipse. Objects that are still close to the focus distance may be just a little blurry. The circles of those points would be so small that they still look like points to us if we view the image from a certain distance and under certain other conditions. But at some distance, the size of those circles gets so large that we no longer see them as points, but as circles. And what I've referred to as a circle is called the circle of confusion. And the largest circle that still looks acceptably sharp to us is called circle of confusion limit. Another important concept is the depth of field. And that term just refers to the range of distances where all points look acceptably sharp to us. So the distances where the circles of points on the image are smaller than the circle of confusion limit. The size of the depth of field is influenced by a few factors, mostly by the focus distance, the focal length, aperture, and of course by the circle of confusion limit. The depth of field can also be split into the near depth of field and the far depth of field. The near depth of field contains all points that are closer to the camera than the focus distance, and the far depth of field contains all points that are further away from it. And the far depth of field is generally larger than the near depth of field. There are some formulas which we can use to estimate the depth of field, and I'll put a link to them into the video description. Now, if we want to take a picture of an object or of a scene that is larger than the field of view, then some parts of it will be blurry. So if we want the entire image to be sharp, then we have a few options. One is to change the distance to the object or the focal length. But that's often not easy or not desirable for various reasons. Another option is to decrease the aperture. But we can only decrease the aperture down to a certain point. If it gets too small, then we hit what's called the diffraction limit, and our entire image gets more blurry. And if we are after really sharp images, then we probably want to pick the aperture where the lens is at its sharpest, which on APS-C cameras and lenses tends to be somewhere around f5.6. Another option is to use focus stacking, where we take multiple images of the same object, but in each image we focus at a different distance. So in each image, different parts of the object are in focus. And then we combine all of those images into one image, where the object that we're interested in should be sharp from front to back. So let's have a look at one way of doing that. First, we have to capture the images. And of course you can do this manually, but that will take a lot of time and the resulting focus positions are not going to be very consistent. And it's also quite easy to accidentally move the camera. Luckily, most of the newer, higher-end cameras have this feature built in. For example, on my X-T4, it's called focus bracketing, and you can set it up quite easily by specifying the minimum and maximum focus distances, and then the camera automatically takes the pictures for you. If your camera can be controlled via a computer, then you can even implement focus bracketing yourself, which gives you a lot more fine-grained control over the focus positions. So ideally, we want to avoid any movement of the camera between pictures. So it's generally a good idea to use a tripod when taking the pictures. If your camera has image stabilization, then I turn that off. Because if your camera is on a tripod, then image stabilization often actually makes images more blurry. If your camera has an electric shutter, then I'd prefer that over the mechanical shutter, because the mechanical shutter can induce vibrations. I usually also lock the white balance settings and the exposure, because that leads to more consistent colors. So let's look at some of the images that I've taken. Even though the camera didn't move, the images do seem to move. And that's due to focus breathing. We've already talked about that a few times in the past videos. It occurs because when we change the focus, then some components of the lens move about. And that results in a small change in the effective focal length. But of course, that's an issue if we want to combine multiple images, because the same points of the object are not at the same places on the images. So we will need to correct it. So after taking the pictures, we need to align them. And this alignment process tries to correct any movements in the images that we didn't avoid when taking the pictures, and it tries to correct for changes in the effective focal length that are caused by focus breathing. There are different software tools that you can use for the alignment. One popular open source program is called Align Image Stack by Hugin, and we'll now look at how to use it to align our images. The way the program works is that by default it takes two subsequent images and it uses the Harris corner detector to find features that are present on both images. And it uses the feature locations and the options that we'll talk about in a moment to reverse the movement of the features. This is done for all subsequent pairs of images. So in the end, all images can be mapped to a common field of view. So to use the program, we first need to pass a list of images, which here is called input files. And that can be a list of file paths, or you can specify a folder that contains the files and then use the asterisk as a placeholder. By default, the program then sorts the images by exposure. That's useful for creating HDR images, but not so much for focus stacking. We want the program to go through the images in the order of increasing focus distance, because that way the overlap of the sharp areas of the images is maximized and the effect of focus breathing is minimized from one image to the next. So we can prevent this automatic reordering by setting the option Use Given Order. On my system, the files, when using the asterisk, the files are automatically sorted by name when they're passed to the program. So the order is correct. If you're not sure if that's the case on your system, then you can add the option -p followed by the name of an output file. And after you run the command, you can open the PTO file with a text editor, and in section Image Lines, you can see the order in which the images were used. Okay, there are a few more options we'll discuss. First, we'll add the -m option, which tells the program to correct for changes in magnification caused by focus breathing. Then we'll add the -d option. This option tells the program to correct for changes in radial distortion. So all real lenses are imperfect, and there are always some distortions. For example, if you look at this piece of paper with a grid on it, then you can see that the lines on the image are not straight, even though they are straight on the actual piece of paper. And that's because of lens distortions. Most distortions depend heavily on the distance from the image center, which is called radial distortion. Just to be clear, passing the -d option doesn't mean that all lens distortions are corrected. It only refers to the changes in radial distortion from one image to the next. We will look at correcting all geometric lens distortions in the next video. Then we can add the -i option, which corrects for changes of the image center across images. The image center doesn't necessarily refer to the central coordinates of your image. Rather, it refers to the center of your lens. And if on your camera the lens is not perfectly aligned with the sensor, then the image center will be offset from the central coordinate. And this -i option looks for changes of the image center across images. If that option is really necessary for your setup, is something that you'll have to test. Then there are two options that influence the feature matching process. By default, the image is split up into a 5x5 grid. And in each cell, the program looks for up to 8 feature matches across adjacent images. With the option -G, we can change the size of the grid, and the option -C changes the number of features to use. If you're not getting a good alignment, increasing these values might help. There are a few more options, but I think we'll stop here. Finally, we tell the program to save the aligned files in a specific folder with the option -A. And if we run this and look at the output, then it looks quite good. The images have been aligned well. Now it's time to combine them into one image. And for that, I'll use another program of the Hugin suite called Enfuse. This one is also open source. And at this point, let me mention that there are quite a few programs for focus stacking. And if you really want to get into, for example, macro photography, then some of the commercial options may be more convenient to use and may give better results than the Hugin suite. But Align Image Stack and Enfuse is definitely a good place to start. Okay, so Enfuse can be used for different kinds of image stacking, and the default settings are not suitable for focus stacking. So we're going to set the following options. First, we define the output file with option -O. Then we set the contrast weight to 1, because the way in which Enfuse determines which parts of an image are in focus is by checking for the contrast between a pixel and its neighbors. Pixels that are in focus tend to have a much higher contrast than pixels in blurry areas of the image. Then we turn off any influence of exposure and saturation on the stacking process, because they're not appropriate to focus stacking but to other applications of Enfuse. Hard mask means that there's a kind of hard boundary, a hard separation between areas that are in focus and areas that are out of focus. As there would be if, for example, you're looking at an object in the foreground that is set against the background that's further away. Finally, the contrast that's used to find the sharp areas of the image is computed on a grayscale version of the image. And the option Gray Projector allows you to specify how these gray values should be computed from the color values of the original image. Luminance tends to work quite well. Okay, there are also other options, but I think these are a good place to start. So if we run this command, then we get this image here. It looks quite alright. One thing you'll notice is that there's a kind of halo around the object. We didn't have that in the source images. So where does it come from? One reason for it is that this area next to the edge of the object is actually never really in focus. If we focus on the object in the foreground, then the object's outline is sharp, but the background is very blurry. As we move the focus further away, the background gets sharper, but the foreground is now blurry and covering a part of the background that would now be sharp. So that part of the image that's right next to the edge is never really sharp, which is causing this halo. Also, I think it's quite hard for an algorithm to decide which image to use in this case or in similar cases. And I think some algorithms do a bit better in some situations and a bit worse in others. And I think dedicated focus stackers use a combination of different algorithms and manual retouching to get rid of the halo and of other imperfections. If you're one of them and you're watching this, then do let us know in the comments how you deal with the halo. In my case, I'm using these images for 3D reconstructions. And for me, the halo is not a big deal because it's mostly outside of the objects that I want to reconstruct. So it doesn't have a big impact. Talking about 3D reconstructions, let me take a little bit of time to show you what I do in my setup to deal with focus stacking. First of all, I'm not using the focus bracketing feature that's built into the camera. My machine controls the camera directly and it automatically sets the focus positions. What I need to do right now is to set a minimum focus position and a maximum focus position once before the machine starts, And then for each physical location from which photos are taken, it automatically takes the necessary photos at different focus positions. One challenge here is that when you set the focus position of your camera via a computer, then you don't actually set the distance in meters, like the focus distance in meters, but you set the position of the motor in your camera that's responsible for focusing. So first I had to set up a calibration to find the mapping between the focus positions of the motor and the corresponding focus distances in centimeters. We can then use that mapping to find the motor positions of the minimum and maximum focus distances that are set at the beginning of the scanning process. Then, using those distances and a circle of confusion limit that we set in advance, we can use the formulas for the near and far depth of field to find those focus positions that minimize the number of photos we have to take while keeping the final image sufficiently sharp. We can set the desired sharpness of the final image by adjusting the circle of confusion limit. A smaller limit leads to a smaller depth of field for each photo and therefore to more photos. And the opposite is true for a larger limit. But in any case, I only take the minimum number of photos required for the requested sharpness. And fewer photos means less computation. Then, I'm not running the image alignment that we saw earlier because it takes a fair bit of time. Instead, I've created another mapping. And if I know the focus position at which a photo was taken, then I only need to apply the mapping to take the photo from the focus position at which it was taken to a reference focus position that I set in advance. And that has two advantages. The first is that just applying a mapping is a lot faster than doing the whole alignment process every time. And second, it means that all of my images, all of my stacked images, use the same effective focal length. Even if the different sets of images were taken at different focus positions, which because of focus breathing means that they were taken at different effective focal lengths. After applying the mapping, they all use the same effective focal length. And that's very useful for 3D reconstructions because the algorithms work better with consistent focal lengths. So, that was a relatively short video about focus stacking. The next video will be a bit longer and it will be about correcting vignetting and lens distortions. We will create our own correction profiles, we will test how well they work, and then we will compare them to some of the profiles that are already available online. So, thanks for watching and see you soon.